So hello everyone and welcome to yet another problem from Geeks for Geeks. The problem is pretty simple. It says check for BST. We are given a root of a binary tree and we need to check whether it is a binary search tree or not. We are considering that the BSTs cannot contain a duplicate nodes and that's our assumption. And you know the properties of BSTs, that left subtree contains all the elements less than the node key, right subtree contains all the node greater than the node key, and the both left and right subtrees must also be binary search trees. This is somewhat a recursive definition of a binary search tree, which will also you'll get into many of the textbooks. But without any further delay, let's start with the examples. So the first example pretty much says that, hey, it's a binary search tree. How do I know this? So let's take this an example. I'll just zoom it in for, yeah. So based on that, we know that the root node is 2, right? And the element 1, which is less than 2. And we go ahead, we check the element 3. We go ahead, we see with the rest of the node. So it means that if this node or this subtree wouldn't have been a binary search tree, the entire tree wouldn't have been a binary search tree. Let's check this hypothesis well. Let me erase all those this. And here we go on the second part. So it seems it is a false statement. Let's check how come. So to check this point, we need to check if this and this. So it's null. So it makes sense that it is a binary search tree, because every null node is a binary search tree itself. So you have a root node as 2. You need to check that, hey, my left is a binary search tree. I will go to the right. We check for 7. For 7, I check that, hey, my right is also binary search tree. What about my left is also binary search tree. What about my right? Same goes for 6. Initially, you know that 6 and 7, they won't be a binary search tree, but still I'm going further. If this is a binary search tree, question mark. And problem boils down to here. Yeah, this is binary search tree. This is binary search tree. So 9 from this subtree is also a binary search tree. Cool. It says it's a binary search tree. So you'll say, yeah, I am also binary search tree. And the same thing would go over here. Yeah. But hey, it says no, I'm not a binary search tree because it's 6, it's 7. Although we can compare it initially as well. So we can check directly first that, hey, check my left and right. And then check my left subtree and right subtree. But this was also good, so let's ignore it for a while. And now we know it's not a binary search tree. So let's check for next problem. Yeah, this is pretty much looks like a tree. So we know that we have checked the initial nodes now. We know that 5 and 10, yeah, 5 is lesser. And we can say that this subtree can be a binary search tree. Okay. What about this? Yeah, this node is very well valid. But what about the subtree? So for checking this node is checked, but let's check the subtree as well. So this is 9. Okay, this is valid. But wait a second. Every node over here needs to respect this. So 9 is lesser than 10. But it lies on the right. So this comes to a point that we cannot go with the earlier intuition we had. We need to have what is our minimum value and what is our maximum value. So within that range only, we can go ahead. So here at the root node, we didn't have any minimum and maximum concept as such. Okay. So I'll take it over here. So we didn't had any minimum and maximum concept as such. So we have minus infinity to plus infinity. So, and when we went further on the left, we are bounded to 10 as the maximum value. so the number cannot exceed 10, and here it is infinity minus infinity as well. So this number lies in, that's why it's valid and legal. What about this? So for this, it was 10, it should be greater than 10 to plus infinity. When it goes left, it should be within 10 to 20, which is not valid, my friend. So if this is not valid, it returns false indication to this node, and this node indicates a false indication to this node, and this node says that, hey, right from this node which you have provided as a root, you didn't found any binary search tree over here. So this is how our algorithm would go ahead, comparing the ranges and checking whether it's binary search tree or not. This is very simplified way upon checking whether a binary tree is a binary search tree or not. So the approach we have discussed traverses at a worst case each and every node. So the time complexity of this approach would be O of n. And about the space complexity, yeah, it takes a stack space. More about this approach will be coding upon. As you can see, it's a very light problem. So without any further ado, let's get into the code. So jumping into the code, let's see how we can deal with this problem. I'll just go ahead and return node or is BST helper, but if you're using Java, something like this, you can overload this method as well, which is good practice, which is also good practice, to be honest. And we'll just say integer dot min value. Why so? Because Java doesn't provide us the negative infinity. Also, we need to provide max value for positive infinity. So once this is done, let's overload this method. So I'll be using boolean because we are directly returning, and this is boolean as well. We'll say is BST. First thing we'll go ahead and take is node root, and I'll take min and max. So our goal is to keep root.val or root.data within min and max, excluded by the way. So as we can see that even duplicates are not allowed, so if root equals to min, that's not allowed. So let's check for this root is equal to null, and if it is null, then yeah, it is a binary search tree. We'll go ahead and return true. What if it's not null? So in that case, we'll check if root.data so lies within the format or not. So minimum and root.data is less than maximum. In such case, yeah, we can go forward, but if it is not the case, we need to not move forward with this. So if it is not the case, like this, we return false. Now assuming if control comes over here, then root data is within the limits. Now we just wanted to check whether left and right is equal or not. Left and right are BST or not. So how do we check this? We check it by using isBST method, which we have created just now. So isBST, and we'll say that, hey, check for left, and you'll say me, okay, he will check for left, but what would be the minimum value? So I'll say the minimum value would be the minimum which you have provided. And what would be the maximum value? And the maximum value would be root.data, because no element on left should be greater than this value. So this is the maximum thing. Similar thing goes with right as well. So we need to check it if it is BST for right node, and when we are checking for right node, we need to consider the minimum value to be root.data, because everything upon the right should be greater than this root node. So this is the minimum value here, and the maximum value would be the maximum which we have sent. So let's check this method, the small method with only 3 major conditions. So it says true for initial test cases, that means our code compiles well. Let's check it for rest of the test cases as well. Well, it seems that our code has been passed for the rest of test cases as well. So this was all about it. It has worked within O of n time complexity on O of height of the tree space complexity. On an average, you can say in terms of an log n space complexity, because it uses recursive stack, and hence it is. So it's been asked in this many interviews, and so this was one of the question from tree. If you wanted to visit more such questions from tree, click the video on your right, and I'll see you in the next one.
We are dreaming in the dark.